So welcome to the Kavli Exoplanet Future Symposium, part of the TESS Science Conference. So today is going to be a little bit different than the past 4 days, if you were here for the past 4 days. We're going to look towards the far, far future of exoplanets, 20, 30, maybe 1,000 years out. And it's going to be a lot of fun. So there's a series of 4 panels. The first is going to start on biosignatures, and then we'll move to planets themselves. Beginning in the afternoon, we'll do planetary architectures, and then finishing up with techniques, how we're actually going to do any of this. One of the key aspects of this, though, is it's not just the panel, it's you too in the audience. And you may not realize it, but you're also being live streamed, so there may be a whole other audience invisible that you can't see. In order to make this all work and let the people online and you in the audience all participate in a flexible way, we have a system called Slido, which will magically appear on the screen here in a second. So Slido is a web-based question system. So this is one of the few conferences you go to that you're allowed to have your phone and be frantically typing away as you go. So if you go to this webpage, you can start even now putting questions in. And you'll see them in a second here start to appear on the screen if you're one of the first questions. And also, in addition to questions, we will occasionally be asking you questions of the audience, of things that you think we might want to know of you. So one could imagine a question like this. When do you think life will be discovered on another planet? Is this happening soon, or is this going to be a long time? So you can log in right now and put in your answer. This also lets you practice. So you can also, the fun part of this too is you get to watch the answers in real time. So usually it's sort of like a popularity contest. The most popular answer starts to attract lots of things. All right, so while you start your voting, so the voting will stay alive and you can continue doing this, and we will get started with our panel. So what we're going to do is we're going to have each of the panelists just give you a few minutes about themselves and what they're super excited about and what they think the future might be like. That'll give you a sense for what kinds of questions make sense to ask the panel. But the bulk of it is going to be the panel talking to each other and you talking to the panel through Slido. So this will be fast, and then we'll get to the discussion part right away. So we'll start with sorry, flip wrong side of the page. Sara Walker, you want to introduce yourself?
Sure. So I'm Sara Walker. I'm an associate professor at Arizona State University, and I'm an astrobiologist and theoretical physicist. My primary interest is actually understanding whether there's universal properties of living systems and how we can identify them, and I work a lot on the origins of life and trying to quantify the origin-life transition. But my interest in exoplanets is actually kind of the inverse problem. If we could actually discover life on other planets, it would give us more window into what the universal properties of life are. But obviously, to find life, we need to know what those universal properties are. So I think that the problem of understanding life and understanding life on exoplanets or at the origin are actually pretty much the same problem. And so I'm keenly interested in basically figuring out what life is as a physical phenomena. And so when you think about it from this perspective, the idea of discovering life as an aha moment on a single exoplanet is kind of a little bit more like a fantasy novel or something, and the actual science of it is a bit more interesting in terms of thinking about how we actually can constrain the probabilities for life on exoplanets and how we can understand what is the likelihood of this phenomena arising on different worlds. And so I think very much cosmologically about the problem, as is shown in this pie chart here, basically how can we actually think about what the likelihood or the probability of life arising on a planet is, and how can we use exoplanet science to statistically constrain that. And so a lot of the work I've been doing is kind of pictured in sort of the bottom right panel here about thinking statistically about the search for life on exoplanets. And so from that perspective, what we really want to do is think about probabilistic biosignatures and also thinking about surveying many exoplanets to look for life and not just thinking about targeting a single planet. And so there's a couple different approaches there that we could talk about in the panel. But one of the things that I've been working on in particular is trying to think about what astrobiologists call agnostic biosignatures nowadays. But biosignatures that aren't so dependent on the chemistry of life on Earth. So how do we actually get around the fact that we have a single biosphere? And so the way I've been approaching that is actually to think about statistical properties of chemistry. And my work has done, or my group has done a lot of work studying statistical regularities in biochemistry across the planet. So thinking about life as a planetary scale process, what are the regularities in the chemistry? And we're doing similar work now on exoplanet atmospheres to think about whether, if you look at the patterns of reactions in atmospheres, are they statistically different for living worlds and non-living worlds, which gets us into thinking about, right now working on hot Jupiters to think about statistically characterizing different chemistries based on the disequilibrium drivers. So there's a lot of different ways of thinking about how to merge the way we're thinking about current exoplanet science and observational constraints and future biosignatures. So working on hot Jupiters now, for example, and thinking about them statistically and how we can actually think about forward about the science we're doing for hot Jupiters as being useful tools for terrestrial worlds down the road. So I'll finish with that.
Off to Shawn.
So I'm Shawn Domagal-Goldman. I'm an astrobiologist and the head of the Planetary Systems Lab at NASA Goddard Space Flight Center. And I spent the last 3 years of my life, hopefully the next 20 to 30 years of my life, thinking about how we might build a telescope that would get the biosignatures that we'll be talking about today, and specifically a space-based telescope. I know that there's some great opportunity in the near term to try to get transit spectra of potentially habitable worlds around M-type stars and look for signs of life on those types of worlds. But I think that we really should think about, and I think no matter which one comes first, I think we have to do the search for biosignatures for planets around both sun-like stars and around the cooler type M-type stars. I think it basically, that helps us get at this question of how is life responsive to its astrophysical context. And ultimately, for the sun-like stars, that's going to require us to build space-based telescopes that could block out those 10 billion photons from the host star so we can see that one precious photon from the very pale blue dot. And ideally, we want to do this more than once because, I'm generally an optimist. I'm a Cubs fan, but I'm not quite that optimistic that the first planet we look at is going to have the signs of life. Now, to do that is going to be really challenging. And the other thing I work on, in addition to working on some of these mission studies, is thinking about what's the community we need to have in place. What does this room look like in 20 years after we successfully build and launch that space telescope? Because we will have that one pixel of light, but within that one pixel, we're not just going to have the atmosphere whose composition we're assessing, and hopefully some surface details we can get at, but also the interactions of those two things, the surface and the atmosphere with each other, but also the oceans and the cryosphere and geological activity, and as we mentioned before, the astrophysical context and what the star is doing to all of those systems. And that's really complicated. And especially for the early career people in this room, what I'd say is that at some point, it doesn't matter how smart you are to be good at this. There's a bandpass filter, right? But if you're writing papers, if you're active in the community, you're passing that bandpass filter. What it really requires, both at the individual level and at the community level, is us finding out how to work really well with other really smart people. Because the smartest person on the planet can't store enough information in their brain to handle all those systems simultaneously. It really takes an integrated, coordinated approach of the community. And I have one more slide, which is, I think, an example of this, although on a different axis, which is we've been studying two different mission concepts that would provide this kind of spectra. Probably not exactly like this, just hopefully as exciting as this one. And if we don't get to the other slide, that's fine. It's
There's
just
an
words.
advancer somewhere.
Okay. So we've got the LUVOIR team and the HABEX team that are both studying concepts that would do the direct imaging reflected light spectroscopy of exoplanets. And a lot of people ask, like, are you in competition with each other? And in some sense, yes, because there's only going to be one of these two missions prioritized by a decadal survey. And there's two other mission concepts, origins and links, that might also be prioritized instead of LUVOIR HABEX. But LUVOIR and HABEX aren't competing so much with each other for two reasons. One, it's not a competition, right? Like we're all studying these things so we have as informed as possible a decision by the Astro 2020 panels. That's the reason we're doing all this work, is not as a proposal, but as a study of a concept to inform the decadal survey process. But secondly, LUVOIR and HABEX, they're two visions of the same goal. They're both doing reflected light spectroscopy of exoplanets. They'll both, by the way, also do some pretty awesome transit spectroscopy of exoplanets, and they'll both do a wide range of astrophysics and solar system astronomy as well. And the difference between them is really their levels of ambition and potentially their levels of complexity and cost that would come with those different levels of ambition. When we're doing these decadal surveys, one of the things we don't know is what's our budget going to be like 5 years from now. And I think personally, as an exoplanet scientist, I really like the fact that we've got a range of options for different launch vehicles, for different cost points, and that based on what we have in terms of technology, launch vehicles, and cost, we can do the best version of this science in the future. So they're working together, and long term, I hope we all find ways to work together once we build one of these things and launch it into space and get the data back. In a room like this, 20 years from now, hopefully. So.
All right, so Paul.
Thanks. My name is Paul Rimmer. I'm a Simons Senior Fellow at University of Cambridge, and I work on astrochemistry, atmospheric chemistry, and some prebiotic chemistry experiments. And when I think about biosignatures, I think about two big questions. One is, are we alone in the universe? And the other is, how did life originate? And the reason I think about the second question, Sara already touched on this, but one of the main reasons is Sarah Walker, David Catling, a handful of other people have come up with this powerful statistical tool that can calculate the probability that a particular molecular feature that we happen to see is in fact a biosignature, is a genuine sign of life. And I think that that's going to be a statistical tool that's going to be very, very useful over the next 20 or 30 years in order to assess probabilistically the sort of reliability of particular signatures on a planet to genuinely be signs of life. Beyond the 20 years, because we weren't given a sort of maximum distance to look into the future, it'd be really neat to take that equation and sort of turn it on its head, kind of exchange prior and posterior in a sort of sense, and actually look at the distributions of planets with signs of life to see what that tells us about which origin scenarios are in fact favored. And so you could imagine a case where you could plot out all of these habitable planets. There'd probably be a lot more dots on here in a certain sense than what's shown here, but this is a sort of representative example, and you could look at it in terms of stellar effective temperature and water content. There are many different things you could plot this on, but if you plotted it on this and you found that most of the planets with signs of life had a low water content, low enough that you'd probably have some sort of surface land, and a high enough effective temperature that you might have ultraviolet light being provided, then ultraviolet light and shallow pools might be important for your scenario. That might be favored. Alternatively, you could have distributions that are insensitive to the stellar effective temperature, but more sensitive to the water content and favor water content up to the point where the water content becomes so great that the rocky surface becomes segregated from the liquid ocean. And if they happen to lie within that sort of region, then that would favor hydrothermal vent scenarios. Or you might find something that doesn't correlate with these particular axes, but might correlate with others. For example, by looking at Young analog systems, you might find out that certain planets were likely to have had a giant impact in their history. Maybe those are the ones that happen to have signs of life, and so that would suggest impact delivery is important. Finally, there's always the chance that after 20 or 30 years of looking, we end up still with a sample size of 1. And this is still informative. This tells us about how contingent origins of life may actually be. It gives you a sort of estimate for that. And this would be especially important if we find life elsewhere within our solar system, and especially if we could determine in the farther future whether that life had its own origin or whether we shared a common origin. If I had to guess, I would guess that life is rare. And that way, if after 20 or 30 years of looking, we still have our sample size of 1, at least I get to be right. And if we find life in many places that we look for it, I couldn't be happier to be wrong. The last thing that I would say is, regardless, it's essential for exoplanet scientists, geologists, prebiotic chemists to develop their own fields and then to build connections between those fields in anticipation for whatever scenario we might end up facing in the future, beyond the next 20 years. So,
thank you.
My name is Rafal, Szabla, and I actually came here from Poland 2 days ago. So I am a Simons Fellow, just as Paul is, but at the Institute of Physics of the Polish Academy of Science. But the thing that makes me a bit different from the first 3 panelists is that I am actually a chemist. The things that I'd like to talk about today is actually what chemistry we could try to simulate in the lab and with computers, and then try to get, with the knowledge we get out of it, back to the observers, to astrochemists and astrophysicists and astrobiologists, and discuss what this tells us, and maybe then get again back to the lab and try to improve our chemistry, so work in this kind of feedback loop. So in the very beginning, what we chemists actually have and what we would like to know before we go to the lab is a wish list. So first thing, which you see on the top left corner of my slide, is actually a wish list. So we would like to know something about the chemical composition. We would like to know whether there is water, what is in the atmosphere. I mean, firstly, is there liquid water? Is the water just in the atmosphere? Are there any interesting molecules, inorganic or organic molecules, like, for example, HCN, which we would like to see because we think that that was one of the important compounds for the origins of life on Earth. Are there any agents that could do interesting chemistry and photochemistry, since my main interest is actually prebiotic photochemistry and the way UV light could have enabled the formation of more complex molecules on Earth. These would be, for example, H2S and SO2, so hydrogen sulfide and sulfur dioxide. Is there any oxygen? Are there any other simple gases? But another thing is actually we would like to know something about the conditions. What is actually the stellar input to the planet? Are there any clouds? Can we tell something about the aerosols, about the sizes of the aerosols and the composition of them? Is there any chemistry in these aerosols? And of course, the temperature. Another interesting question, are there any other sources of energy, like electric discharges, which could induce the chemistry? And what we do, and the way we can help, is the very easy thing in the very beginning. That's actually something that we already do, is we try to simulate the signatures which allow us to identify the spectra of the molecules on exoplanets. So that's quantum chemistry, which we try to employ here. But we also can simulate the chemistry. As you see the surface there, it tells us about the energetics of a chemical reaction, so we can figure out what's the barrier, we can figure out what's the rate, and and if the products are favored. And we can also collaborate on this together with experimenters. And a very interesting experiment that Paul is doing is actually StarLab, in which he tries to simulate the things that I do with supercomputers in a lab, using a very good light source, which actually simulates the input of the young sun, which is a xenon lamp. And an example which you can see is at the bottom of the slide. So we would like to start having some knowledge with, let's say, HCN and H2S, which we know are poisonous, but they were unlikely poisonous to the early life. And then see if with these conditions we can get some more complex organics, like the second cluster of molecules which you see. And then, knowing these products or intermediate products, we could try to ask a question, okay, can we observe them? Can we find some signatures of these compounds? If not, is it just because our instruments are not as good, or there is any other reason why these volatiles are not there, but they still could be? And in this feedback loop, we could possibly construct a map of chemicals that would be available on an exoplanet, and maybe they could actually, with this chemistry, build some what we would like to see RNA precursors or precursors of some other informational polymers. I think the most distant question, which we could ask right now, because all of the things all of the things which I just talked about seem not so far distant, is actually, can we find a way of detecting these much more complex organics, which not necessarily will be in the atmosphere? And can we find some different informational polymers? And I think that a very interesting way of at least figuring out the more complex organics and whether they could become informational polymer would be coming back to Enceladus, because in these plumes we know that there are many interesting complicated organic molecules, but the instruments that were used on the Cassini probe were not advanced enough to actually resolve the molecular structure of them. So I guess, again, just as other speakers suggested, it would be really nice to come back to what we have in our solar system and work more and figure out more what we have here.
Great. So on to Janusz.
Yeah, so my name is Janusz Petkowski. I work at MIT. I am a research scientist there. And essentially what I am interested in is one question. Does life really have a choice? And what I mean by that is essentially that if we actually think about it, the physics is universal. No matter where we go, we will have the same laws of physics in the observable universe. We can say the same thing about chemistry, essentially. The periodic table is essentially everywhere the same. But unfortunately, we do not know how does it translate to biology. We don't know if our life that we have here on Earth is some general plan that always has to be this way. And so basically, we don't know really if chemistry of life has to be exactly as it is on Earth, always, everywhere, elsewhere on exoplanets. And that's actually a very important question, because if we are actually to look for life on exoplanets, we might ask a question, are there any chemical features that all life has to exhibit, no matter where it originates? And we don't know that. Life on Earth produces thousands of biosignature gases, and there are thousands that, in principle, could all accumulate in an atmosphere. There are thousands more that actually could be explored by life elsewhere. We don't know which ones we would encounter. There is always a possibility, and this is work of Shawn, that we are haunted by the possibility of false positives. But what I would also say is that there is also a danger of false negatives. We might find life, and we might not recognize it that we found it, because our understanding of chemical repertoire and possibilities of chemistry for life is simply too narrow. So what we are quite interested in is we are trying to find out the general chemical rules behind all life. And essentially, we want to find life's preferences, life's limitations, and life's choices. And how do we do that? Well, we try to employ a big data chemoinformatics approaches to this. We create a very large repositories, databases of molecules that life makes, and we apply all kinds of sophisticated statistical analysis on those data sets, and we try to find patterns in life's chemistry. I will illustrate this with a very, very simple example. Essentially, if you look at this, we have two elements that are biogenic elements here on Earth that life heavily relies on. One is nitrogen and one is sulfur. If you actually combine them together and form a bond between them, and form a nitrogen-sulfur bond, this bond actually is very rarely explored by life. This chemical functionality is very rarely explored by life, despite the fact that it's actually a nice bond which can be easily made. It has very nice chemical functionalities. It is actually a backbone of pharmacological industry on Earth here. But life doesn't tap into that at all. And life has all these preferences and also has these limitations and some sort of gaps in chemical space. We would like to understand what are the rules behind life's journey through chemical space and what we would expect if we had, for example, different conditions on other planets, which actually would somehow change the chemistry of life as its origin. This ties very well to Rafal's work, he is interested in pre-biosignatures. What would happen if the collection of pre-biosignatures that we have, or the initial chemistry from which life originates, is a little bit different? How that would translate later on the chemistry of life that we have later, after its origin. We don't know that. We have no idea. We would like to have that knowledge at some point. This is a gargantuan task. There are many, many environments that we have to explore. There might be even an environment which this NS chemistry is actually favored to a certain degree. It's not here on Earth, but it might be elsewhere. We might go even further and ask a question, is water the ultimate and only solvent in which complex organic chemistry can happen and life could arise? We don't know this. We ask those questions, and we asked those questions decades ago. The answer to that question is still not here. I hope, and I really hope, that in 40 years, or maybe 60, or hopefully not 100, we will have answer to this. And we are now currently starting to answer these questions. We are employing a very sophisticated, hopefully sophisticated, data mining, big data approaches and all this. So this is also the convergence of multiple sciences at the same time. Big data analysis, computer science, and also chemistry, and hopefully at some point, laboratory experiments. We would like to test if chemistry can be, for example, if complex chemistry can function in different solvents. We don't know that. So in 40 years, when I retire, I would like to know if life really has a choice. That's essentially when I will stop. Thank you very much.
Thank you. So those of you who have been going online will see that lots of people have been putting questions, so you will get to see on screen. The panelists haven't gotten to see what the questions are coming up, but I've been watching. Yes, they're very small print on the front of the page. They're all frantically looking back. But there are 3 different question threads that are all asking about Habex and Louvois. Many of them are phrased in the negative of, what if they're not selected? What will we do? But I want to phrase it to the panel in a slightly more positive way. What can you do with Habex and Louvois? And are there other things you could do with other instruments, even if they didn't happen?
So what you could do with Habex or Louvois, Habex is designed, and I didn't get into the I talk about different levels of ambition, but Habex is being designed so that we've got a really good chance of over 95% chance of taking a spectrum of at least one potentially habitable exoplanet, so one rocky planet in the habitable zone of a sun-like star. The yield estimates is actually we'd get more than one. We get somewhere in 10 to 11 of those spectra, depending on the version of the architecture version you're talking about. Louvois wants to do the same thing, but it wants to do it 30, 40, 50 times, again, depending on which version of Louvois you're talking about. And the driver for that is that we want to do it for Louvois enough times so we can start to get at some of these statistics that we're talking about. You probably couldn't say with Louvois, what percentage of water-based worlds have biosignatures, but you could say what percentage of rocky planets in the habitable zone have water or have biosignatures, or have water and biosignatures. You can do that one axis of analysis. And if either one of those is prioritized, it's going to mean a lot of really cool things for our community of people thinking about biosignatures, because then we're going to have to build these things and design them around those science cases, which means that the agency, NASA, is probably going to invest a bunch of research into making sure we do it right. And that'll probably happen starting pretty early on to make sure that the architecture trades and the technology development we're doing in advance of the real ramp up in the engineering team that would happen sometime in the mid-2020s, that we do all that front-end stuff right. So that would be good. I don't want to just not address the negative side to that, since it was asked at least once or twice. If neither one of those is prioritized, it depends, right? I mean, if the Origins telescope, which is one of the other missions, is prioritized, that also could do some pretty good biosignature science with transit spectroscopy of planets around M-type stars. And we've got the ELTs that are also going to be doing that kind of science. And so a lot of the same science questions are going to be there. They'll be a little bit more focused on, and they're going to be focused in the near term this way no matter what, on planets around M-type stars. So those questions about how is habitability affected by the high energy radiation from those host stars, those are all still in play. And then folks that really want to do the sun-like stars, we keep working for another decade, and we try again for the 2030 decadal survey is probably what ends up happening.
Could I ask a quick follow-up question off of that? Actually, so let's say that we can only really look at these M-dwarfs, which will definitely be true in the near future, and depending on how funding situation goes, may be true in the far future. These stars have very different activities, and maybe they also have very different activities going into the past.
Yes.
Would this be sufficient still to get a large enough sample size so you'd at least be able to do some sort of distribution statistics, try to figure out if certain populations favor the more active ones or the more quiet ones?
So I'll be honest, and if anyone else here, even in the audience, has a better answer, more knowledge on this. My impression is that for most of the searches for biosignatures around the M-type stars, the sample size is probably not going to be it'd probably be more similar to what Habex is going for, and less like what Louvois is going for. I've also heard some pretty definitive statements from a lot of the people making models of atmospheric escape in these high energy environments that are like, if you've got this history of high energy radiation, like you shouldn't have an atmosphere, period. So, it might just take the one counterexample to upend a lot of those expectations. For me, the important thing is, especially for the M-type stars, because those stars can be as different within the class, as different from each other as they are from the sun. Having a diversity of M-type stars for that search, I think, is going to be really important as we think about these things. And the very first question, which JWST might even be able to get to, is do they have atmospheres at all, and do they retain them in the context of that high energy radiation?
Yeah.
Is that
no? That's I think that's a good answer, and it does point to something that we do need to answer in the near future. And part of the problem of looking too far into the future is it's always contingent on things you find before.
Right.
If we find that around all active M dwarfs, there's pretty much no surviving atmospheres.
Right.
That'll be sad, but that will also say something about what we'll be able to look for in the future.
Yeah.
All right, so there's, unsurprisingly, so the people in the audience have been coming from a workshop where you're talking about all of the different types of stars that things are going around. So you mentioned M dwarfs and whatnot. So one of the questions that's percolated to the top is, what about the stars themselves, stellar characterization? What do you need to know about the stars in order to figure out the life around the stars and the search for habitable zones?
So I'll start briefly. So there's a paper which I published with Jianfeng Su, John Sutherland, Ed Gillen, and Didier Queloz and Sam Thompson, where what we did is we looked at what's called the sort of abiogenesis zone, where all of these sorts of things are going to be very dependent on the sort of scenario that you're looking at. But at least under these sort of scenarios where you need UV light and where you need hydrogen cyanide, there's a sort of rate at which these sorts of things can happen. And one of the things that then you can actually look at is how much light do you actually need for the chemistry that we see in the lab to work on the surface of a planet around one of these kinds of stars. It turns out that if you are looking at quiescent emission from these different stars, you need at least K dwarfs in order to actually run this sort of chemistry. Maybe stellar activity can help and run this sort of chemistry for the particular M dwarfs. But that's just one example for ways in which that sort of line can be cut. And Shawn mentioned another one, which is if atmospheres end up being transformed so that they're uninhabitable anymore, or if there are no atmospheres, then that's another sort of limit for what sort of stars you would want to look for life.
And I mean, to follow up on what you just said, this is actually, someone could ask, I mean, do we need UV light? So at least when we look at prebiotic chemistry in the conditions of the early Earth, if you would like to synthesize selectively specific biomolecular building blocks like fragments or even precursors of fragments of DNA or RNA, or some particular molecules that could take part in metabolytic cycles or cycles of high energy intermediates, you actually need this UV light to synthesize them selectively and efficiently. And I don't think we have any other efficient and high-yielding synthesis of many of these molecules which does not involve UV light. So we can create some part of it, but at least not the whole prebiotic inventory that we think that we had on the early Earth. And that's why I completely agree with Paul that one of the key factors could be actually the spectral range of the star and actually how much ultraviolet light it emits.
Go ahead, Janusz, that's fine.
Thank you very much. So I actually have a different question or request to astronomers. I would like to know what is the distribution of elemental abundance of stars in general. What elements we can actually detect there, and how different our sun really is. I am a biochemist, yeah, so I mean, I would like to know how does the elemental abundance, really how constrained it is. Because if we can have a very, very different distribution of elemental abundances in the star, and if it actually translates to then the building blocks of the planets around such star, and if that in turn skews the prebiotic chemistries or Rafal's pre-biosignatures, this would automatically skew and the origin scenarios for life. So the very simple question, a statistical representation of the elemental abundances of as many stars or solar systems in general would be a very, very useful thing to have. We have a very, very limited information on that in the Hypatia catalog, as far as I remember, but we need much more data on that, and that would be actually very useful. Yes.
So actually, I guess my point is going to tie some of the things that you guys said together, which I think one of the things that, like the question was originally about what kind of stellar properties should we look at, and I think that's good, but it tends to be very anthropocentrically biased in the sense that both Paul and Rafal were talking about origins of life on Earth, or at least biopolymers as we know them on Earth, which I think is important to consider what kind of conditions those could be formed on other worlds. But as it stands now, at least for me personally, the field of origin of life itself is too anthropocentric, and we have a tendency to highly design and engineer experiments for specific biopolymers that we think are present in life, rather than doing exploration, random exploration, more of what Janusz is advocating of chemical space, right? So if you imagine you could design origins experiments that weren't saying, a priori, we expect these molecules, we want to engineer an experiment to get these molecules, but you see what comes out of random chemistries under certain planetary conditions, that starts to feel much more like origins of life to me, and actually exploring chemical space for life-like chemistries. So if you re-envision origins of life that way, I think there's a tighter connection between exoplanets and origins of life science, in the sense that what we really should be doing is looking at the diversity of planetary compositions, the diversity of stellar types, thinking about the possible chemistries, mineralogies, environmental conditions on other worlds, and designing those into our origins experiments. Right, so we should think about origins of life as a broad phenomena that happens in chemistry sometimes, like much more like an artificial life approach, as people do it in that field, not so much in astrobiology, but just asking the generic question, how does life arise from non-living chemistries? Experiments should be designed from that perspective, and then those become much more useful for exoplanets because we have a broader chemical space possible. And so I think what should be happening in the next 20 years in particular is much more focused discussion between exoplanet science and origins of life science, and thinking about origins of life as a planetary scale process that happens on certain planets and not others, and how do we actually understand the mineralogy and chemical composition of planets that give rise to living systems. And that's actually experimentally tractable here on Earth. So I think people don't think about exoplanet science as an experimental science here on Earth, and we need to start thinking about it that way.
Yeah, I mean, I think that both actually have a very
this
important connection.
was your point originally, yeah.
Yeah, and I think that this is especially important because it may be that actually there's only one chemically determined pathway to get to life, and so it's very important to explore what we know, because then at least we have a better chance for success there. It would be wonderful, and in fact I think it's quite promising that there may be other pathways and other polymers and everything else still doing the exploration into the region that we don't know and the region that we do will be very, very useful, because then we can compare those. And we can eventually, in the far future, compare the sort of distributions of what we see and say, oh, the way that life started on Earth is really favored everywhere else, or perhaps there's something quite unique about life on Earth. That maybe the biopolymers were, that there are some biopolymers that were more preferred, actually, and we just happened to get the ones that we did. And I think that would be a really interesting thing to find out.
Yeah, definitely. Yeah, so I think the approach of using like prebiotic chemistry and things that we know on Earth and connecting them to exoplanets isn't wrong. It's a great starting point, but I think that we need to expand our space was my only point. I think what you guys
completely agree.
Yeah.
So there are a series of questions on there about, other types of chemistries and other sorts of habitable zones. What other types of chemistries do you think are possible, and what other sort of habitable zones would you look for?
I'll start with the least creative answer, probably on the stage, which is the way I approach that question, and I'm biased because I'm trained as an earth scientist, as a geologist, is to look at the past versions of Earth that we have recorded in our rock record. And these aren't time machines, right? These are all proxies that someone like me is waving their arms with a model to explain as much of the geological data as possible. It's actually not too different from how we're eventually going to explain a biosignature on an exoplanet, right? It's inherently limited data about a very complex planet that you're explaining as much of as you can at one time. But if you look back in Earth history, we have ample evidence of life on Earth 3 billion years ago. We have ample evidence that oceans were present 3 billion years ago. And we have, I would argue, ample evidence that there was no oxygen around 3 billion years ago. So then this gets into that false negative question of, if we looked for just oxygen and methane and ozone, we wouldn't have found life on Earth before the Great Oxidation Event 2.5 billion years ago. That's about half the history of the planet. It's about a third of the history of life on Earth. There's a whole other geological period for another 2 billion years where the oxygen was still lower than today. So I think about just starting there, we've got data on ancient Earth that we can use. We've got models that explain that data. We can use that to say, what else could we identify Earth's ancient biosignatures with? And there's great work by Josh Chrysanson-Totten on this, actually suggesting that even Webb could identify a Archean Earth-like planet. The key is you have methane that's still being produced by methanogens at the surface of that planet, and there's methane on Titan a lot. So methane on its own is a very poor biosignature. But if you have it in the context of a lot of carbon dioxide, Titan does not have as many oxygen atoms in its atmosphere as Archean Earth, we think, had. So that combination, that methane in the presence of those oxygen atoms in the form of CO2, we think to be a strong biosignature. Now that's just that's not saying that's not thinking outside the box, that's just thinking about the old box, as well as the one that's staring you in the face. So and I'm sure other people on stage have more creative ideas on how to find alternative biosignatures.
So,
go ahead. Yeah.
I think part of the question was also related to, should we actually limit our definition of habitable zones to the zones where we have liquid water? And this comes very quickly to one of the points that Janusz made, that actually could we have another solvent that could sustain life? And we discussed this a bit yesterday, but I think that actually if we think and consider another solvent, it still would have to be or it would be very good for the chemistry at least, that the solvent is a polar solvent, because chemistry in non-polar solvent actually is not that diverse and versatile, while polarity allows to differentiate the chemical reactivity, and it allows us to go into many interesting chemical valleys that we wouldn't, for example, go into in conditions as, for example, we have on Titan, where we have lakes of methane and ethane. So I think this is a great question. I mean, is there any other solvent that could sustain life? And we discussed ammonia yesterday.
We discussed all kinds of scenarios because essentially, if you think about it, you can imagine a separate habitable zone for each of the solvent. We think about the habitable zone where, for Earth, is simply defined with respect to the liquid water and sustainability of liquid water on the surface of the planet, but each of the solvents has its own habitable zone, so to speak. I am the optimist in this crowd. Rafal and Paul are more skeptical regarding regarding the possible diversity of chemistry or complex chemistry. I think that we need more experimental work in this area. These questions were asked very, very long time ago, and very few people actually rigorously tried to answer those questions in the lab. We even lack reliable information on such simple questions like how likely it is that a non-polar cryosolvent like methane is going to solubilize complex molecules. We think that it is unlikely, but we don't know because insufficient experimental data is available. So this is an area of research that is completely unexplored, and yet it is actually crucial, because recent studies, theoretical studies, but recent studies actually suggests that the possible diversity of seas on the surface and oceans on the surface of exoplanets might be huge, and those seas could be built from solvents that are completely different than we have here on Earth or even in the solar system. So this is something which we really should answer. I know that Rafal is skeptical about the non-polar solvents, but I would say that, yes, maybe he is correct, but we need more experimental validation of this, I would argue.
Yeah.
So I'll give the most radical example, I guess, since Shawn started with a simple example. But before I get to that, I just want to. So I think there's an inherent assumption that life is chemical, and I actually agree, or at least life emerges in chemistry. I think that that's probably actually accurate for the physics of origins of life. In particular, because my personal bias is that life has something to do with information and the physics of information, and information probably does emerge in chemistry. And so I think there's legitimate reasons for that, but then you can ask, well, how general is that kind of physics, the physics of chemistry that gives rise to life in chemistry? And just to give an extreme example, there was recently a preprint posted by Lee Cronin's group at University of Glasgow on a molybdenum wheel that can do autocatalysis. So these are like self-reproducing chemical networks, which we think as being characteristically living, right? So your body actually reproduces itself by a collective set of molecules that can reproduce themselves, right? So this is how you sustain yourself. So imagine just having a system that only has molybdenum in it, makes macromolecular structures, and actually can reproduce itself as a collective system. So this has actually been discovered here in the lab on Earth. But if we think autocatalysis is a fundamental process for life, this really expands the kind of chemistries that we can think about life being possible. I'm not advocating that I think there's molybdenum-based life out there that just uses that as a foundation of its chemistry, but I think having these kind of examples is really useful for thinking about, if we have like metal-rich worlds or something, like what's possible for the different chemistries, and that we really do need to think more outside the box about what we're talking about when we're talking about what life is and how broad we think the phenomena is.
Clearly, our audience thinks that beer is a good solvent for life.
I think that the feedback from the audience is extremely useful. I mean, we might start our first experiments starting from coffee, I guess, relatively soon.
Well, beer is a good biosignature, apparently.
Caffeine is a very good biosignature.
Yeah.
Yes, I agree. We are in full agreement here. Yes, absolutely.
But there's another question, so switching back to questions of how do you incentivize experimental research in different solvents?
Industrial applications probably would be my best guess.
Also send a mission to Titan.
There you go.
And
Yeah.
we're about to do that, right? Like I'm super excited that we're sending a drone to Titan to fly around and do some more analyses of the chemistry that exists there, right? That is so essential to this whole discussion in my mind. I actually think if I were going to do an experiment or a mission to probe this further, it would not be an exoplanet mission next. Right? I mean, we can do an exoplanet observation of the ethane, methane habitable zone, but I think the next step is actually to go to Titan, go back to Titan and study. And fortunately, we've got plans to do that. So.
But I actually agree with what Sara said, and this is a very good point. I mean, the potential, the industrial applications of exploring chemistry in different solvents might be actually something which would be extremely useful. And if we can tie our exoplanet and theoretical biochemistry research into something which will generate revenue, then it would be phenomenal. So yes, I completely agree. We might actually come up with some sort of ideas of industrial applications of this research, and this would actually help a lot. Yes.
I think that a very interesting avenue is actually also synthetic biology. And there are many interesting developments in it. I don't know if anyone actually tried to do some self-replicating systems or some compartmentalized systems that could, let's say, almost live in different solvents.
In silico, yes. That's the problem, because we live, unfortunately, in water environment at certain temperature range. So these experiments, these chemical experiments that explore the chemistry in different solvents are actually also technically difficult to do. Because if you try to do experiments in liquid nitrogen, well, unfortunately, everything is evaporating as you do the experiment. So that is something which there are certain technical limitations which we would have to solve first. And so this ties into this future question. We probably would have to design a specifically tailored systems to actually address this question very well and rigorously.
Yeah, there's been just a little bit of theoretical work going back to Titan about acrylonitrile being a potential way to form vesicle-like structures within
azotosomes.
Yeah, exactly. Yeah, so lots of fun things to look into in the future.
Which are unfortunately thermodynamically unstable.
Yeah.
So that's
that spoils
sad.
all the fun. No,
Sorry?
I'm just kidding. I said that spoils all the fun.
Yeah, but it was really fun. It was really a fun concept. But I mean, was, but maybe is, hopefully. I mean,
Yeah, well, the thing is, you want to go there and see what actually happens.
Test
You
that.
want to go into a lab and find out whether you
Yes.
make these sorts of vesicle-like structures with these kinds of molecules.
Absolutely.
So switching it back to planets, one of the other questions was, do you need a sea of this solvent, right? Just like we had seas of water, and how would you get that sea of whatever it was, of beer, on the planet?
You would have to, should I start?
Sure.
Some solvents are clearly more abundant than others. So certain solvents from the pure abundant, cosmic abundance case are at a disadvantage. So you might need a situation in which a certain solvent, for example water, gets removed during the process of planet formation. And then obviously a certain other solvent might actually substitute it. There are many, I mean, you could imagine a situation in which water gets lost, yes, during planetary formation. I mean, it's a question to a more planet and astrophysicist-oriented people on the panel, but I could imagine that. So people could actually try to model that, how likely it is that you would actually get a certain solvent having a stellar condition of that type, for example. Because it might very well be, for example, that, and I'm sort of making stuff up now, that M-dwarf planets might actually have higher probability of having seas made of, I don't know, liquid carbon dioxide, for example, and not water, yes? And this would, for example, mean that certain stellar types would have a higher probability of life arising, maybe, who knows, in a completely different scenarios. So that's my take on it.
So now I'm going to give the unromantic practical answer, which is that for the challenge for a lot of this, whether it's a different solvent or for thinking about non-global oceans of the solvent, is that in a theoretical sense, we can think about how those things might work, but in a practical sense, if you actually want to observe it across interstellar space with a telescope, you need the signal to be large, both from the ocean or the solvent you're looking for and from whatever life is occurring inside that solvent. And this is the reason why we focus on the habitable zone, the global liquid water ocean surface zone, because we think that we know that water works. There's a follow the water strategy in the solar system, so we're expanding that to the exoplanet search. But also that global surface thing. Europa could have life. Europa-like planets or moons in other solar systems could have life. But how would we find it, right? Europa is not big enough to retain an atmosphere to hold the signal we could look for in it. It's also far away, which means it's dim, and thus it's going to just be harder to observe in general. But the habitable zone brings a lot of practical observability benefits to it as well. And it's not to say we shouldn't think about it, or 100 years from now we couldn't build a telescope that could look for it. But for this first generation of missions and telescopes, we're probably going to be focused on water globally at the surface.
You start with what you know, and you branch out from there.
Yes. I say it's not like the drunk looking for their keys under the spotlight. I say it's me saying that, if you lost your keys, I'd say, look in your couch cushions or in the jacket you wore yesterday, or, because that's where I lose my keys.
Yeah.
And chances are if I gave you, the 10 places I tend to find my keys the next morning, most people in the audience would probably find their keys there, too. I'm not going to get everyone's keys, but I'll probably get a bunch. Just on my experience, or shared experiences.
All right, so before we switch to another question, I saw a technical question go by. If your outsiders are trying to figure out how to watch the live stream, there's a link at the top of the conference webpage, tsc.mit.edu. And now we'll switch back to a science question. So a lot of people are wondering, all right, so we're looking for life. What do we do next? Which also begs the ethical question, should we be finding life given what we're doing to life here?
Safely far enough away, I think, if we're looking for exoplanets, that we probably won't affect their economy very much. But I can't think of any ethical problem with looking for life on exoplanets. I can think of more ethical problems looking for life in our own solar system, but I'd be very interested in whether other panelists have
I think the
other
ethical
things.
concern is more for humanity's interpretation of the results, finding life on another world, than thinking that we're going to actually, travel to these exoplanets in any reasonable time scale and affect the life on that planet. And then that's a question for humanity to assess what it means to not actually be alone in the universe. Although I think that's more of an academic discussion. I remember having a conversation with one of my car salespeople at one point who thought life was on Mars. So I think, which is just to the general point of most people aren't even really cognitively aware of the fact that we don't know about any other life in the universe, right? They just have this vague conception, we haven't discovered aliens, but if they never really thought about it deep enough to think that, oh my God, we're alone as far as we know, right? So I think we have to really think very carefully about how to bring that news to the public and how to have that discussion, which, to Shawn's point, is part of a global discussion. But as far as the scientific discovery itself, I think probably, at least from my perspective, what's likely to happen is we're going to have a result that's suggestive but not conclusive. And it's going to be, probably a few different kinds of signatures and a lot of modeling about the planetary context and things that goes into it. A lot of smart people working on trying to understand that system and then inferring that there's probably an inhabited world, but we have some kind of minimal confidence about whether it's inhabited or not. And then there's going to be a ton of people that just fixate on studying that system, understanding its chemistry really well, understanding its history really well, and then trying to really tweeze out whether or not the hypothesis that life is on that planet or is on planets in that system as being the right one. Right, so this is part of the scientific process that I think is something that exoplanet science is really bringing to the forefront about the search for life that hasn't been in our historical narratives about how the discovery of life is going to go. And we really need to get in our mind that it's going to be much more like the discovery of the Higgs, where we have some hints or something, and we start refining our search space and starting to build up our confidence that there's actually that kind of process happening there. And it's going to require on the same level of international collaboration. And I think that the community just really needs to get in that headspace to think about how, A, the first detection is going to go, and then B, how are we actually going to handle it as a community and really confirm definitively that we've discovered life and make that announcement to the public. Because when we make that announcement, we should be pretty darn sure that we've discovered life.
Do you think that we will be very darn sure that we
I think, so for me,
for a particular object,
no,
rather than
I personally don't think for a particular object, right? But again, it's interesting that you pointed that out, because even though I'm the biggest advocate, it's not going to be a single object, my narratives still go to that, right?
Okay.
So I think it's just because we have these implicit biases when we think about life that I think are really hard to get around. And part of it's because we're life, so we think it's very obvious that life is, a really, we should immediately recognize life when we see it. But I always like to point out to people that we actually understand more about the physics of the atoms in your body than you as a collection of atoms in a living entity. And I think that part is really hard for us to really understand, that we don't understand ourselves at all. And so I personally think the discovery is going to be more like if we get LaVoir going and we have a statistical survey, that we have some suggestions that are planetary formation models, and all the modeling we put into it aren't predicting exactly the distribution of atmospheric composition that we would expect. And maybe we should start thinking about the deviations as being signatures of biospheres on those worlds. And probably to that point, what I think is important is one of the things we have to think about in our search is how common or rare life is. So if life is very rare, it's not, LaVoir's not going to pick up that signal. We're going to need the next telescope that can do surveys of thousands of exoplanets to really pick up that signal. And so what we're really going to be doing is sort of bounding the likelihood of life, the probability of life, which is another reason for thinking about it statistically, is if we don't find life on a planet, and we can at least be sure that we don't have a biosphere that's driving the dynamics of that planet, then we actually have a scientific result, right? It's not the result we necessarily wanted, but it's a result. And we need to start being able to bound how likely we think life is to form on worlds that we think have the potential for life to form. And so trying to constrain that, right now we basically have no constraints on whether life is common or rare. But if we start surveying thousands of exoplanets, we see no evidence of life, then that starts to suggest life is at least reasonably rare. And that's also an important result to have.
So what tools do you actually need? So you actually have a question from the future panels from later this afternoon. What do you actually need in order to do these searches?
To do the follow-up searches or the searches for life?
For the searches for life. You're the life panel. So what do you need to search for life? I'm biased, right? I gave my answer in the intro. I think we need the direct imaging we need spectra, right? Because you're only going to get the chemical information that you could infer biosignatures from if you're taking the wavelength-dependent information from the planet. Because you could also do it by looking for forests or chlorophyll or something like that on a map, but that's much harder to do than getting the spectra. So you start with the spectra. And you can do that with the transit method or with the direct imaging method. I think that the direct imaging method is better in a number of ways, not the least of which is the thing I mentioned before, which is it gets you a different class of stars. I think the question of what do you do
after you find the biosignature and you've got the argument in the community and in the literature of what to do next, I actually think we don't really know. I mean, one thing I'm confident of is some graduate student somewhere is going to be up all night the night after the press conference and we announced we found life, running a model that says, no, you didn't. Like, it's this geological or astrophysical process that you weren't thinking about in this, even if it's this like, specific perfect combination of parameters that I can make oxygen and methane and water without life, like that, someone's gonna write that paper, within a month or two of the press conference. But then, this is something you said, Sarah, like at that point we're at the scientific method, right? It is, that paper should make a prediction of if it's this other combination of processes, these are the distinguishing observable characteristics of it. And the people that are, on the discovery team are gonna be like, well, if it's life, then you're gonna see chlorophyll, or you're gonna see, oceans and continents, like whatever it is, you can go to that next set of observations to discriminate between the competing hypotheses.
So then what instrument after this direct imaging instrument would you need in order to make those kinds of follow-up?
I think in my mind, there's probably at least 2 or 3. The 2 most near term are probably after you build a LUVOIR or a HABEX. There's that joke from Contact, right? Why build one when you can build 2 at twice the price? You could build multiple LUVOIRs or HABEXs and use them as an interferometer. And then you could actually get a map of the surface. You can actually get multiple pixels across the planetary surface. The other thing you could do, and the thing that I think is actually more achievable in the near term, you probably need to do this from a technology development standpoint first, is to build an IR interferometer and do direct imaging, but do it at a complementary wavelength range and go into the infrared, because then you can tease apart questions about the planet's climate that you a little bit better. You'll get complementary greenhouse gas and biosignature information in the infrared. The infrared is just full of awesome, people from Sara's group and Janusz have worked on this. Like, there's awesome spectral information in the infrared. So you could do wavelength complementary, or you can try to get the spatial information. The third thing, which I think would probably happen less, is you build a huge rocket and a tiny instrument, you send it to that star system, and a really good, accurate communications
and patience
package and patience, and you do a flyby. But that's probably the third of the 3. You probably do the IR spectroscopy, direct imaging, and then you do the mapping, and then you probably do the flyby after that. I guess. But it depends on what that grad student writes in some ways, right?
Yeah, that's true.
Other thoughts? Other tools you want?
So I think Paul suggested
the
moon telescope, right?
I like the idea of the moon telescope, but I am very much disconnected from instrumentalists, so maybe this will be a good chance for me to find out what the sort of problems would be with this. The main reason why I think that a moon telescope would be neat is it would be something that would be connected to a rock, and so you get a lot of stability. And if you want to do this very high resolution spectroscopy, which has been shown to be very, very promising for finding certain biosignatures, then having it where you don't have much of an atmosphere in the way is a huge advantage.
Yes.
But I'm kind of wondering whether that would be a better advantage than having your 2 or 3 LUVOIRs, or a better, well, you could definitely combine that with the sort of infrared proposal.
So my understanding of the constraints of this is that the nice thing about being in the middle of space is that it's actually really stable, probably even more stable than the moon is in a sense. Like the moon is more grounded in a very literal sense, but you still have micrometeorite impacts hitting the moon, and that is going to impart some degree of instability into your system. For LUVOIR and HABEX, you want to actually have the primary mirror stable on the tens of picometers level. So any vibration you're inducing into the system is going to be bad, and it's going to have to be canceled out. For the moon, most people what they're thinking about doing is to build radio arrays on the backside of the moon. And that, I didn't mention this, but this would be the 4th follow-up, right? Is if the hypothesis is that there's life on planet LUVOIR 7D, right, or HABEX 7D, then the next question a lot of people are going to answer is, what kind of life? Is it intelligent life, especially if there's oxygen in the atmosphere? So the test for that hypothesis would be, let's see if it's sending any sort of communication out, either in a directed or a non-directed sense. And the historical way to look at that has been through radio telescope arrays. And you could build a giant one on the moon, and it'd be actually fantastic.
No, I think that would be really cool, and also for figuring out something about magnetic fields on planets and various other things. But
yes.
Does that mean that LUVOIR is going to have the ability to do this kind of very high resolution spectroscopy and look for, say, even sort of isotopic fractionation and other things that have been proposed for this this kind of method?
It wouldn't be able to do isotope fraction. It can do deuterium and hydrogen for escape from a planetary atmosphere, and I think HABEX can do that for the most favorable cases. Okay. But you couldn't look at, say, like the carbon-13 to carbon-12 ratio in methane and CO2 and look for a biological fractionation of carbon isotopes between the inorganic and organic medium like that. I don't think anyone's done the calculation of what that would require, but bigger than LUVOIR. Yeah. Is what that would require. Yeah. And significantly bigger to the point where I don't think we're thinking about that one yet.
Yeah, and that would be the other advantage of building something on the moon is you can build it piecemeal instead of having to launch one very expensive thing. Yeah.
If we have a moon base and like people are like living there full time, that changes the equation in a bit, and maybe the conveniences that provides overweighs the stability stuff I was talking about earlier. Yeah.
So we're sort of now answering the question, you have now detected life on another planet. Clearly, this next step is to build a moon telescope. And look out. Are there other next steps? What would you do if you found it?
Right, so I was going to answer the question, what should we do to look for it, but also this is what should we do if we find it? Because we've been focused mostly on observations and building telescopes, but there's still a lot of science that we need to do to understand like generalities of life on Earth, which Janusz talked about, and then both Rafal and Paul were talking about origins of life experiments, and I was advocating for this also. That I think the more we can understand sort of what kinds of biological processes or living processes we should expect in certain environments, and the more that we can try to de-anthropocentrize that understanding to the specific chemistry and environments of life on Earth, the better prepared we will be for interpreting data from exoplanets. And so one of the ways of doing that, obviously, is to think about the origins of life as this sort of more general process that happens on planetary surfaces. But we also need to understand how biology's various metabolisms have evolved coupled to the planet, and what are the contingencies in that process, and how can we think about what's the likelihood of having certain kind of metabolic modes on certain kinds of planets. And so that's actually where it really requires exoplanet science to make contact with origin science, evolutionary biology, synthetic biology, and all kinds of other fields that need to be brought in to really understand what is life as a planetary scale process, because we're going to be detecting life as a planetary scale process. We're not going to detect life that hasn't had a global impact. And so we really need to think about the evolution of biospheres now, in some sense, and not just the evolution of individual organisms. And so I think that really necessitates a new kind of science as far as thinking about what biochemistry is, what it does to a planet, and how we can think about the coevolution of biological processes and planetary processes. And so in Exoplanet Biosignatures paper, I guess that was over a year ago that came out now, Future Directions, there were I think, 15 co-authors that wrote this paper on this kind of Bayesian framework for statistical approaches, but one of the things was actually trying to understand those conditional probabilities to really say, this is the stellar environment, this is the planetary composition we expect, and then this is what we expect for the properties of biospheres in that environment. And that part is really where the biology and new approaches to understanding life need to come in. And so I really advocate for more of that kind of science, which requires big data approaches, big science experiments. We need like a Large Hadron Collider scale experiments and funding to really do that kind of science right, especially on the origin side.
If I may, I have one comment. What to do next when we actually find life? Yeah. Well, this is a wonderful time when the birth of new science is going to happen. It's a comparative astrobiology. Yes, we will finally, assuming that we will be able to characterize this life in a certain way, we will finally be able to actually compare our life, its biochemical capabilities, to the life that we've detected, the new one. And then we will finally be able to point, okay, what are the similarities, what are the differences? This would be the fantastic way of constraining this space of possibilities that actually life could possibly have. So that would be a phenomenal thing. So this second, and then we would be able to ask the question, is this really the question of a second origin? How likely it is, that these two lives, let's say that we discover life in the solar system, how likely it is that this life originated completely separately, and how likely it is that it actually originated through panspermia, and we all have common ancestor in this solar system. So yeah, essentially it will be a birth of comparative astrobiology. I am now a regular astrobiologist, but hopefully, yes. At some point in my career, I will switch again and I will become a comparative astrobiologist.
That's the dream,
That would be a phenomenal time in my career. Yeah.
That's great.
Yeah, I just wanted to add, also based on what Sara said and what Shawn said, that It's very easy to ask the question, what will we do next when we find life? But I would also be careful about the wording. I mean, will we have 100% certainty that we actually find life?
It's a probabilistic process,
it's a probabilistic process. So if we can say that there is life with 90% certainty because we see these biosignatures and we ran these experiments, that's actually pretty good.
By the way, the other answer to this question is retire. I'd be ready to retire if we
Have a really big party.
Yeah.
I would
like
go
that
to that
idea.
reception, yes.
Well, and so retiring implies that you're giving up. I mean,
No,
there's
as an individual.
Oh, as an
just-
individual.
I don't mean as a field. Let the next generation of grad students prove me wrong. That's fine, or us wrong, or whatever.
Yeah.
That's.
But there's a question on that. Would we ever stop looking? Right? What looking for the next 100 years and we still don't see anything? Will we just keep pushing harder?
I'd want to keep
We
looking.
would always need a bigger telescope. We know that.
Always.
Yeah.
Yes, so that's...
Whether we find life or not, we'll always need a bigger telescope.
Whether we find life or not, we will always need a bigger telescope. So the search will continue indefinitely.
Our history of searching for life on Mars would suggest, we'd keep looking.
Yeah.
Well, I think there's always the innate curiosity, and there's always the open question that maybe we just really haven't figured out what we're looking for, and aliens could really be so sufficiently alien that all our best, methods of trying to not bias ourselves by our own kind of life might not be successful. But I also think, 100 years' time, say we've been doing these exoplanet searches and we still haven't found life, but synthetic biology or artificial life approaches have advanced so much that we really do understand more about generically what life is and how likely life is to exist in materials, then it might be that we keep pushing the search because we know it's not completely impossible for life to exist in different chemistries or for life to have different properties, or we have some idea that if we design an experiment, we can make life emerge with this kind of probability. That doesn't say anything about the spontaneous emergence of life because we're still intelligent agents designing the experiment, but it does say that that's a physical process that can be repeated, which suggests that we should continue the search.
It also might lead to reanalyses of the data that already exists
Yes,
from the prior search.
exactly. Right? So I think there's the search, but it can't be decoupled from the science we're doing here on Earth and other areas. Totally. And also in particular, in our artificial intelligence also, as far as that field advancing and understanding the likelihood of different kinds of intelligences in the universe, that we need to really be thinking about what other fields are doing as far as how we think about how we construct our search for life.
I remember, I'm sorry, I remember, I think it was 2 years ago, so on one conference there was a survey done, where would we actually find the first alien life? Is it going to be Mars? Is it going to be Titan? Is it going to be is it going to be Exoplanet? And I believe that there was also an option brought by Steve Banner at that time. And he said that we are going to make it in the lab. Yeah. So that option, and actually that option, and this got me thinking, because it is actually not that crazy to think about. I mean, if we understand the biochemical process and chemical processes well enough, we actually might be able to do that. And we might actually create something which is chemically sufficiently alien that it would be considered a separate origin from the purely chemical point of view. Yes, so definitely, it might very well be that we will create alien life in our own laboratories 50 years from now.
So on the 50-year point, I want to wrap up by asking you the same question that I asked the audience at the beginning. How long do you think it'll take? When do you think the first discovery of life out there will be?
It depends how lucky we are.
Well, it also depends on how rigorous our standards are, right? I mean, Gil Levin would argue that the answer to that first poll question is -50 or something like that, because he still thinks he found life in the Viking data. And this is, I saw another question I was just going to touch on. I watched the Allen Hills meteorite press conference recently. I rewatched it on YouTube, and they actually did a really good job explaining the fact that we weren't sure that there was life in the Allen Hills meteorite from Mars. The one thing they didn't do is they didn't do the thing that Sarah's been talking about, which is they didn't tell the public that we won't know if this is the moment that we discovered life for probably 20 or 30 years. Because what the ultimate test is not going to be that first paper. The ultimate test is going to be that if you poll the science community 20 years later, do they believe that discovery was the first? right? So, and you have no way of knowing that in the absence of time machines at the moment of the discovery that's the moment. It's really the test of time that's the ultimate test for whether or not we're alone.
And I could just build on that point for a minute, which is like, so since I'm trained in physics, I always like to draw analogies from like major physics experiments, but it seems to me like with the Higgs and gravitational waves, like those were major discoveries, right, when they were discovered, but we had really good indication they were there before like the official announcement, because we had done all that prior work leading up to it. And so for me, I think about a reasonable timescale, like pending the fact that we don't know if there's any life out there in the universe. So I'm completely agnostic about what the timescale is because I'm not 100% sure that we're not totally alone because there's no evidence one way or the other. But barring that, I think a reasonable timescale for thinking that we might have some rigorous constraints on how likely life is probably about 100 years, right? Because it's gonna take a couple generations of telescopes to really build up the methodology, have like the scientific community across the life sciences and thinking more about the biological side of astrobiology, really getting on board with how to do their science for exoplanets. And then, like the feedback between those communities, developing better methods, that process is probably gonna take, the next 50 years, and then you think the discovery comes after that. So I think we're on a long time scale here, and we have to think over a long time scale. And just for like my physics analogies, I mean, Einstein predicted gravitational waves like 100 years before they were detected, and there was a really good theory and a lot of motivation for that. We don't even understand what life is. We don't have a theory for life, right? So we really need to be working on this problem from all fronts right now if we want to be able to make that discovery in 100 years. And so I think that we really need to think very quantitatively and critically and rigorously about how to do the search, thinking on that 100-year timescale now, if we want it to be in 100 years. Otherwise, it's going to be 500 or 1,000.
Anyone else?
Well, I would say it's quite likely that, for example, with the JWST, we will get already some hints of pretty good biosignatures, but I doubt it will be clearly conclusive that it's certainly life. But these will be already interesting results that could give us some hints. So I would say we will certainly learn more within 20 years, and we'll get some ideas, hopefully, and possibly about pre-biosignatures and biosignatures, while detecting life is a more distant question because, we need very solid data and much more advanced instruments to do it.
So that's actually a very, very interesting point, because Rafal is suggesting that our discovery of life is going to be a gradual process.
Yes.
Rather than a single event that is going to be transmitted all over the planet. So that's actually an interesting point. We might just basically collect a lot of data and then prove life statistically, which is going to be, it is possible. Yes, absolutely.
Yeah. So following up from that, if it turns out that life, like the life on Earth, is very common, then I think that statistics maybe in the next 30 or 40 years will be good enough to say, we won't be able to say this planet has life, but we'll be able to say, out of these 100 or so planets, one of them almost certainly has life. If, on the other hand, life is very rare, or life is common but not like what it is that we're actually looking for, then I'm much more with Sarah Walker's sorts of timescales. And then if it just turns out that we are alone, then it doesn't matter how long we look for other life.
That's why I said
and I am completely
agnostic.
I am with you. I'm completely agnostic about which of those options it is. But the neat part is I, or my children at least, won't have to remain agnostic for,
That's good.
All right. With that, let's thank the panel.